Okay, welcome to lecture. Sorry about that. Computer was doing some updating and stuff. Bad spot. All right, so we're going to be doing chapter 3.12, which is nomenclature. So I hope you can see that. And feel free to type here into the chat box. The notes also should be up on Canvas just in case you didn't see them. They should be up there if you need to go get them. All right, so we're going to talk here about nomenclature. So like I said before, this is going back to chapter 3. It's the last part of chapter 3 there. All right. And hopefully everybody can see it okay. Yes, it's full screen, I hope. Yes. All right. Okay, perfect. So we're going to talk about how to name everything pretty much. And we're going to go through all the different types of naming. So let's get going on that. That is obviously a periodic table. And obviously important with naming, as we've talked about before, when we talked about the periodic table, especially with ionic sort of naming. Remember that there are certain elements that based on their position will basically make a certain sort of fixed charge. And just to review those, again, everybody here in group 1 will be +1. Everybody here in group 2 will be +2. When we come over here to aluminum, it's going to be +3. And remember that for group 4 here, we sort of skip it. And coming backwards where our nonmetals are up in the upper right, we go -3 here for group number 5. -2 and -1 coming this way for group number 7. Remember that our transition metals usually have a variety of charges or variable type charges, but zinc and cadmium there in the transition metals, so these two guys here, will always have a fixed charge of +2 no matter what the situation is. And if you hang a left over here to silver, silver will have a +1 charge. So that's sort of like a backwards L here coming this way. Those three guys there, although they are transition metals, they will have fixed charges of +2 for the zinc and cadmium and +1 for the silver. Again, everybody else there in the transition metal region will have a variety of sort of charges. Also a little bit outside the transition region in this area down here as well. Those guys will have a variety of charges, even though they're not technically transition metals, but they also will have that sort of variable type charge. Okay. So let's talk about then sort of how we go about naming these different types of compounds. We're going to start with ionic compounds. And ionic compounds, as you remember from bonding, is between a metal and a non-metal. And if you remember from bonding that these guys pretty much will have a transfer of electrons. And what that does is for the metal creates a cation, which is something that is positively charged. And for our non-metal creates a anion, which is negatively charged. Again, it's that electrostatic attraction that holds that together. And again, no sharing of electrons in this deal. So when we have just cations and anions sort of by themselves here, this table here shows us sort of the way that we go about naming them. So if it's a cation, we pretty much just use the whole name. So H plus would be the hydrogen ion, lithium, Li plus would be the lithium ion. So we just, pretty much just use the whole name. We do put ion usually at the end of it if it is by itself. So this would be the sodium ion, the potassium ion, all the way down here, our aluminum ion, and so forth. Now, when we go to name an anion that's by itself, or an anion in general, we use basically the root of the name there, but we do drop the last part and put the IDE at the end of it. So fluorine becomes the fluoride ion. Chlorine becomes a chloride ion. Bromine becomes the bromide ion, and so forth. You could also see that hydrogen is one of the only ones that could actually go both ways there. So hydrogen that comes first, and in most cases when you see it, will be H plus and would be the hydrogen ion. When it becomes negative, it can become negative and has a -1 charge. It's known as the hydride ion. And usually this would result in hydrogen coming second after a metal. So if it's attached to a metal, it typically will be negatively charged because, again, the metal would be positively charged. But in most cases, it will be that H plus. So we have our positive guys, which are cations, so just use the whole name. We have our negative guys, which we put the IDE at the end of it. And, that's how we get something when we put those together, like NaCl. We get sodium chloride as terms of the name when we do put those two guys together. So let's talk about type 1 compounds. And by the way, as we talked about with ionic compounds, just a reminder that when we do put ionic compounds together, we always want to balance out the charge in the formula, right? So all the positive guys and the negative guys need to equal 0 when we do that. So when we have something like sodium ion and the chloride ion and we put it together, we just need one of each, and that gives us NaCl. When we write a formula for something that's ionic, we never have a charge, but it is indicated that this thing is made up of two things. It's made up of our cation, which is our sodium, and it's made up of an anion, which is, in this case, our chloride. So we always want to balance charges. So as we talked about when we, for example, if we took calcium and fluoride, in this particular case, when we put it together, we have +2 here, we have -1 here. So if we just put it straight together just the way it was, we would end up with a +1 charge. So to balance it, we do need two of these guys to balance it. -1 gives us -2 and our +2, and our correct formula would be CaF2. Again, overall charge here is 0, but it is still made up of a cation, which is this guy here, and an anion, which is, this guy here. And we really talked to why that is when we were doing bonding. If you remember, when we did bonding, the purpose of that is calcium needs to lose those 2 electrons, right? So in order for it to properly lose those 2 electrons, it needs not 1 fluorine, because only 1 fluorine could take 1 electron. So it needs the 2 fluorines basically to take both of its electrons. And then that gets everybody, as we talked about with bonding, into that noble gas configuration. So everybody's perfectly good in terms of that noble gas configuration. So when we talk about ionic compounds, sometimes they're broken up into type 1, type 2. And type 1, again, is an ionic compound. It's a metal and a non-metal together. Same deal as we've been talking about. We're going to have that transfer of electrons from the metal to the non-metal. And again, that's going to create our cation, that's positively charged, and our anion. Now, in this case, when we look at this to try to determine, and whenever you have an ionic compound, it's always the metal that's really important. The metal here is going to be from group 1 on the periodic table. Group 2, or group 3, which is basically aluminum, or it may be zinc, cadmium, or silver. And what all these guys have in common is what we were talking about at the beginning here. What they all have in common is they all have a fixed charge. So as soon as you sort of see somebody that is a metal and a non-metal, A, it tells you it's an ionic compound. B, what it tells you is when you see the metal comes from that group 1, group 2, or group 3, or zinc, cadmium, or silver, that it is this type 1 compound. And when we name these guys that are type 1, we essentially will use the whole name of the metal. So we just use the whole name of the metal. And then the non-metal gets the IDE at the end of it. So we drop the last part and just put the IDE at the end of it. So again, if we looked at something like we saw earlier, or NaCl, when we look at Na, it's a metal, Cl is a non-metal, Na is group 1, so we use the whole name for Na, which is sodium, and Cl is chlorine. We drop the last part and it becomes chloride. If we look at CaBr2, again, when we look at this is calcium, which is group number 2, means it has a fixed charge. And we use the whole name, which would be calcium. And Br, which is our non-metal, we drop the last part and we put the IDE at the end of it. You will also notice that this 2 here has no effect on the name. People, for some reason, always when they see something like that, want to go dibromide or something like that. And you do not use any prefixes like that. So if you have like a 40 there at the end, which you probably won't, but you know, if you had any type of number there, it will have no effect on that non-metal name. You just simply would name it based off of the element, and it would just be bromide. So if that was a 3, it would still be just bromide at the end. You shouldn't put any type of prefixes in there. Any questions on that there? So here again is a table where we do have our fixed sort of charges, and as I included in there again, our zinc, our cadmium, which are +2s, and again our silver there, which is +1, also have fixed charges. So if we had something like we had a name and we wanted to write the formula. So if we had lithium sulfide, right? So if we had lithium sulfide, for example, we wanted to write the correct formula. Again, we would go to the periodic table. We see lithium as group 1, which automatically tells us it is a +1. We would go to periodic table and find sulfur, which is group 6, would tell us it's a -2. And again, when we put this together, we want no charge. So in this case, we do need an extra lithium over here to get us +2 to balance out that -2. And we should end up with Li2S as the correct formula. Now, some people will tell you that, you know, you could just do what is sometimes referred to as sort of the crossover move, where if you have something like this, you know, you could bring that down, or even if you have the formula given to you, you know, you could go this way and that way in terms of figuring things out. And yes, it does work. It does work a lot of times, but it is not 100%. There's a lot of cases where if you just simply not think about it and just cross over, you will end up with the wrong formula, the wrong charges and stuff like that. But, you know, if you're good at 93% of the time, it's probably good. You'd probably be okay. But it does work a lot of times, but not 100% if you kind of do that crossover move. Any questions there on group 1 or type 1? So why don't you take a couple minutes here, or a minute or two, and come up with the correct names for these guys. And while you're at it, I'm going to give you some names and write the right formulas for. So let's see what we got. Let's do. All right, so names on the left and on the right. Why don't you write the correct formula for barium oxide, magnesium nitride, and aluminum sulfide and see what you come up with. Okay, so let's see how we're doing. Let's start with the first one. So again, when we look at this, that's K, which is a metal, potassium, and Cl, which is a non-metal. So we know that this is going to be full name there for the first one, which is potassium. And chlorine becomes chloride. The cation would be K plus the formula for it. The anion's formula would be Cl minus, right? So that would be our anion and our cation. So again, a couple of things about that. If you're asked to write the formula for the ion, the cation or the anion, as you can see, again, they both have charges included. If you're asked to write the formula for the compound, again, no charges when you put it together. Coming here to our next one, which is Zn, which is zinc and sulfur. Zinc is a transition metal, but it is one of those three that does have a fixed charge, and that is basically zinc with a +2 charge. Sulfur, which is group 6, has a -2 charge, which is why when we put it together, we only need one of each. So because zinc has a fixed charge, we just call it zinc, whole name, and sulfur becomes sulfide at the end. Coming down here, we have Ca and Br2, which we named earlier, and that was calcium bromide. Again, calcium being group number 2 has a fixed charge, And as we saw earlier, a +2 charge, and Br, which is group 7, has a -1 charge. And again, lastly here we have Ba, which is barium. We have H, which again, remember, is technically a nonmetal. So there's still a metal and a nonmetal together here. So Ba, which is barium, whole name. And what that means is barium is +2 here, which is our cation. And our anion in this case is actually the hydrogen, and the negative form of it would be our anion. And that's why we need 2 of them to balance out the charge. But when hydrogen is negative, it becomes hydride, IDE at the end of it. Any questions on any of those names there? Okay, so now if we have the name and we want to write the formula, you basically just kind of work backwards. So when I see barium oxide, I know barium is group number 2, which means it has a +2 charge. Oxide, which is oxygen, which is group number 6, has a -2 charge, which means when we put these together, we just need one of each, and we should end up with BaO as our formula. Coming this way, we have magnesium, which is group 2. That's a +2 charge. We have nitride, which is group number 5, and a -3 charge. Again, when we put these two guys together, we basically need to balance out the charge. We have 2 on the left, 3 on the right. Common number is 6. To get magnesium to 6, we actually need 3 of them. And to get nitrogen to 6, we need 2 of them. And again, that basically means we have 3 of these magnesiums at +2 each. So if you just drew all 3 of them out, that's basically 2, 4, 6. We have 2 of these nitrogens at -3 each, gives us -6 and +6. We get our correct 0 in an overall charge to balance it out. And lastly here, aluminum sulfide. Again, aluminum is group 3, which means it has a +3 charge. Sulfide, which is group 6, has a -2 charge. Same deal here. When we put these together, this is going to need to be 6. So we need 2 of the aluminums and 3 of the sulfurs. And again, this means that we have 2 aluminums at +3 each. That gives us +6. We have 3 of these sulfides, each at -2, gives us -6, and we're balanced. These are 2 cases or so where you can do the flip in terms of the numbers, and you will get the right formula. This is a case where it won't work really right. If you did the flip down and the flip down, you would be putting 2s here, and that technically is not the right formula. So it should be BaO. So again, kind of doing the crossover move does work most of the time, but not 100%. So again, it's best to know how to balance it out and everything like that. Yeah, it should equal 0. Yeah. So you do want to make sure everything equals 0 when you put it together in the formula, if that's your question. Is that in reference to the last one? Yeah, so remember that whenever you do put them together, you do want it to make sure that it balances out and equals 0. And really with ionic compounds, they really are empirical formulas. So really what that means is when we put them together, it's basically the simplest way you could get to 0. And that's why technically speaking, our top guy here, if you put the 2s on the bottom, would be incorrect. It's not really the correct way that they would come together. They would come together there with a 1-to-1 relationship. Why is there's a 2 and 3 subscript for the last one because aluminum is +3? and sulfur is -2. So when if you just straight put them together like this, there would be an overall +1 charge. So it couldn't be 0, 0 because one's +3 and one's -2. So basically you need to get both of them to 6. In order to get aluminum to 6, you need 2 of them because each one's +3, so that gives you +6. And to get the sulfur to 6, you need 3 of them because each one's -2, which gives you -6. Other questions on that? You're welcome. Okay, so that is type 1. Let us then talk, I think, about type 2 compounds. So type 2 compounds are also ionic compounds. They're also metals and nonmetals. And same deal here, no sharing of electrons, just a transfer of electrons. And much like type 1, the important part of this sort of setup is the metal. The metal here will be a transition metal, are just to the right on the periodic table. So those are guys in that area. If you look on the periodic table, somewhere around lead, tin, antimony, in that sort of area. And those are guys that are kind of below the staircase on the periodic table. And below the staircase on the periodic table, those are metals. Above the staircase, they're non-metals. So even though they're technically not transition metals, they are named kind of the same way. And again, here, these guys have a variety of charges, except for obviously these guys here, which we just talked about earlier. But again, in this area down in this region, these guys are also named sort of the same way. And what those guys have in common is they have a variable charge. And because they can make different charges, so for example, copper could be +1, copper could be +2. If you have iron, it could be +2, iron could be +3, depending on the situation. And because they do have that variable charge, the way that we name these guys are kind of the same way as we did type 1. We still use the whole name of the metal. We still use our non-metal that has that IDE at the end of it. The difference is in the middle, we do put a Roman numeral. And we put a Roman numeral to indicate the charge on the metal. And that means the positive charge on the metal. If you took one of the metals out, what the positive charge would be, not how many metals we have, which is a very common mistake people make, is they use the Roman numeral to indicate how many they have. But it's actually, if you took that positively charged metal out, what the individual positive charge is on it. So for example, if we did have something like FeCl2, in this particular case, when we look at it, we do see a metal and a non-metal. But when we look at iron, it is in the transition metal region, which should indicate that you do need to figure out what the charge is. The good news is, although you may not be able to determine the charge off of the metal right away, you will always know the charge of whatever it's attached to. So Cl is group 7, which means it's a -1 charge. And there's not just one of them there, there's actually 2, which means overall we have a -2 charge for the negative part of it. And we know that to balance it out, this guy would have to be +2 in that case to balance it out. And that means that we would call this full name of the metal, which is iron, Roman numeral 2, again, not for how many we have, but for the actual charge that's there. And the last part is named just like we did in type 1, even though there's 2 of them there, it is just chloride, IDE. And again, that would be different if we had FeCl3. In this particular case, same deal. We have 1 iron, but in this case, we have 1, 2, and 3 chlorides. And that's a -3, which means in this case, +3 this has to be, which means this guy would be iron, Roman numeral 3, chloride. Again, the +3 here on the metal is where the Roman numeral comes from. So really the naming part here is just telling people that in this particular case, we're talking about the iron with a +2 charge, while say in the other case, we're talking about an iron with a +3 charge. So your transition metals are the guys that could do that. And again, just to the right of the transition metals, like our lead, our tin, which is SN, or antimony, those guys are bismuth. They typically can have Roman numerals as well, and should have Roman numerals as well. So as we see on this chart, and as we talked about, pretty much everybody in this transition metal region will do it. Everybody over here will do it. The 3 that I scratched out here are the ones we talked about previously. And again, that is your zinc, your cadmium, and your silver. Even though they are technically transition metals, they do have fixed charges. And that means that you should not use Roman numerals for zinc, cadmium, and silver, but everybody else is a transition metal. And to the right there, you should use them. Now, for the most part, we will use, not really for the most part, we will use these Roman numerals here. So you can see chromium 2 in that first case, chromium 3, and also if you had the ion by itself, that's how you would name it, chromium 3 ion, chromium 2 ion. Mercury is kind of a weird one. It might be a little hard to see here, but this here and this first one here, where it has all the 2s, the +2 and the 2 on the bottom, is actually Mercury Roman numeral 1, while the one that has just the 1, 2 is actually Mercury 2. So Mercury is kind of a weird formula. Mercury 1 is basically 2 mercuries with a +1 charge that are together. So that's why the 2's on the bottom. And that's also how you could usually determine if you're talking about Mercury 1 is in the formula. That 2 will still hang out there and you'll see it, as opposed to down here, no 2. And that usually obviously doesn't end up in the formula either. So Mercury is kind of a weird one. Now, we won't use really these common names, and sometimes you will see these common names, sort of the old school way of naming things, and they use OUS or IC to name. And in the case, for example, of copper, they'll use cupric for the +2, and they'll use cuprous for the +1. And iron, they'll use ferric for the +3, which has a larger charge, and OUS for the one with the smaller charge. Oops. So we really won't use these type of namings here, but sometimes people still use them. And that's sort of the way it works. The one that ends in IC has the larger positive charge. And the one that ends in OUS has the smaller positive charge. And they obviously are named sort of from the roots of their sort of historical names as well. So why don't you take a second and tell me what, and figure out what the name of this guy would be. So take a second and figure that out. All right, so looking at this one here, again, lead is not a transition metal per se, but it is one of those ones that does need a Roman numeral just to the right. We would look at our oxygen here, which is -2, and this means that this would be lead 2 oxide, again, to balance out that charge, the 2, where our Roman numeral comes from. Any questions on that there? Again, another one, if you sort of did the switcheroo there, you may think it's a 1 and a 1 situation, which is obviously not the correct charges. So again, that kind of switch over move won't work perfectly 100% of the time. All right. So you got a few here. Why don't you, why don't you write the names for those, and when we give you some names, you can write the formulas. Let's see here. All right, so I want to see the names on the formulas on those guys on the right. Chromium 2 phosphide, nickel 4 sulfide, tin 2 bromide, and lead 4 oxide. Okay, let's take a look and see how we're doing. So here, let's see. We got CO, which is cobalt, which is a transition metal. Cl, which is chlorine, which is a non-metal. So again, the key here is our metal part. That automatically should tell us we probably should figure out the charge on it. So we have 1 cobalt, not sure what the charge is, but we do have 3 of these Cls, and that means 1, 2, and 3. That's a -3 overall. So to balance that out, our cobalt has to be +3, which means this would be cobalt Roman numeral 1, 2, 3 for the charge. And again, just going to be chloride, even though there's 3 of them, has no effect on the name. And again, that is what the Roman numeral there is for. Going down to our next one, again, we see Cu, which is copper. That's a transition metal. I kind of wrote right over it there. We have our I, which is a non-metal. Again, automatically going to tell us we need to figure out that charge. I, which is group 7, is -1. So to balance that out, it must be +1, which means our name here would be copper Roman numeral 1, again, for the charge. And it would be iodide, IDE, for our iodine. Looking at our last one here, we have SN, which is tin. Again, not necessarily a transition metal, but just to the right in that area that's basically named the same way. So we're going to look at our BR, which is group 7. And there is, again, if you want to kind of draw them all out, you don't have to, but maybe it's helpful. All that together has a -4 charge for our BRs, which means, again, to balance it out, our tin has to be +4, which means this would be tin Roman numeral 4. And again here, even though there's 4 of them, no prefix, just bromide. Any questions on any of those names there? All right, so when you're kind of putting it together with from the name like we have on the right-hand side, you want to just basically take the basic parts and put them together. So chromium Roman numeral 2 basically tells me I have a Cr with a +2 charge, so that takes care of that. Phosphide is phosphorus, which is group number 5, which means, again, it has a -3 charge. So when we put these together, we want to end up with no charge. So since chromium there is +2 and this guy's -3, the common number there is 6. So to get chromium to 6, I need 3 of them. That's basically 3 + 2. So +2 + 2 + 2 is +6. To get phosphorus to 6, I just need 2 of them. And again, that's going to be -3 and -3, which obviously gives us -6. So +6, -6 overall charge on this guy. When we put it together, no charge. And that's the correct formula. Same thing coming this way. Nickel with a Roman numeral 4 means I have a nickel with a +4. Again, that is what the Roman numeral stands for. Sulfide, which is group 6, has a -2, which again, in this case, when I put them together, I actually need more of the sulfur to get me the 4. So I actually need not 1 of those, but I do need 2 of those, which means this formula would be NiS2. 1 nickel at +4, 2 sulfurs each at -2 gives me -4, and I will have my correct formula there. And here, tin Roman numeral 2 means SN with a +2 charge. Bromide, which is bromine group 7, is a -1 charge. Same thing here. When I put this together, I need more of the Br, so I actually need an extra one to balance out the charge. And that means if I just write what I got there, I have 1 tin and 2 bromides. And lastly, here on the bottom, lead 4 means I have a lead with a +4 charge. Oxide, which is group number 6, has a -2 charge. In this case, I need not 1 oxygen, but I need 2 of them there to balance it out. And that gives me PbO2 would be my correct formula in this case. And again, that's another one. If you did the crossover move, you would not end up with the right formula as well. Any questions on any of those names or how to write the formulas? So again, the two important things to sort of remember for ionic compounds, when you put them together in the chemical formula, there should be no charge. If you're asked to write the ions individually, like the cation or the anion, they should have charges. So if you're asked to write the anion for the first one there, the Cl minus, you would write Cl minus. And by the way, that's what you would write for this one here, even though there's three of them. If you were asked to write the anion formula, what I'm circling is exactly the thing that you should write. You shouldn't write something like, Cl minus 3 or something like that. So you should just write Cl minus. And cobalt with a +3 charge is what you would write there for our cation. Any questions on any of that there? So that's type 1 and type 2, again, both ionic compounds. Let us continue down our nomenclature path. Here's just a little decision tree to help you out, whether it's type 1 or type 2. And again, pretty much with our ionic compounds, it is going to be that metal that's the most important in terms of how you go about naming it. So let's talk a little bit about polyatomic ions. Polyatomic ions are basically groups of nonmetals together. Actually, go back to the right slide there. Let's try that here. Groups of nonmetals together. So for example, if I took something like NH4NO3, and if I broke this apart, I actually have two polyatomic ions. This guy over here is NH4 plus. And that one nitrogen, the 4 hydrogens are all together, and they have a +1 charge. And this guy over here is actually another polyatomic ion. This is NO3 minus. That one nitrogen and the 3 oxygens are all together and has a -1 charge. So these are ions, and they're kind of interesting because, as you may remember, you may have seen this guy. This guy is really something that is covalently bonded together, sharing of electrons. You remember from Lewis structures, that's what this guy looks like. Overall charge +1. And if you also remember from Lewis structures, these guys are sharing electrons. And again, this overall thing has a -1 charge. So these are covalently bonded guys together, but they move around as a unit because they are sharing electrons. So the nitrogen, the hydrogens will never fall apart because there's basically sharing electrons and are bonded together. Just so happens this overall thing has a +1 charge, just like this nitrogen. 3 oxygens will never fall apart because they're sharing electrons. So they always move as a unit. But as a whole unit, this guy has a +1 charge. This guy has a -1 charge, which is why when we put it together in the formula, we technically only need one of each. And each of these guys have a special name. This is what is known as the ammonium ion. This is what is known as the nitrate ion. And when you put them together in a name like this, you basically just use both of those names in this case. This would be ammonium nitrate. So polyatomic ions are groups of nonmetals that are actually covalently bonded together. But as a whole unit, because they are bonded together through sharing of electrons, as a whole unit, they have an overall charge. So they basically work as an ionic compound. And for the most part, as we will see in just a second, this right here is probably one of your fewest, if not only, positive polyatomic ion that you will see, which means in most cases, the polyatomic ion is going to be negative, and in most cases, they are going to be hooked up with a metal usually. Which means we fall back to our normal rules about the metal. If that metal is group 1, 2, or 3, zinc, cadmium, or silver, then you don't need a Roman numeral, and you would just use the name of the metal and the whole name of the polyatomic ion on the back end. If that metal is a transition metal or just outside of that, like we were talking about, lead, tin, you will need a Roman numeral like we did before. And again, you just use the whole name of the polyatomic ion. So in most cases, probably 9 times out of 10, your polyatomic ion is going to be hooked up with a metal. And basically you follow kind of the same type 1, type 2 rules when you go to name these guys. So here's a list of some of those polyatomic ions. And let's do a little correction on some of that I see there. What we got going on here? So I'm not sure why this 4 is on top here, but it actually obviously shouldn't be that. So it should be NH4 plus. 4 got up on top for some reason. Everything else I think looks okay in terms of that. So the good news, bad news is, you know, you gotta like memorize these, yes? So you need to memorize the formulas and the charges that go with it. And there's some ways that you could kind of help yourself do that. There are groups that are related to each other. So for example, if we look at SO4 2-, that's sulfate. You look at SO3 2-, that is sulfite. If you look at NO3-, that is nitrate, as we just saw. NO2- is nitrite. Now, again, this SO4 2-, the 1 sulfur, the 4 oxygens all stay together, has a -2 charge. The SO3 2-, the 1 sulfur and 3 oxygens all stay together, has a -2 charge. The only difference between these two guys is the number of oxygens. The one that ends in the most oxygens ends in 8. The one with the least number of oxygens ends in ite. And we see that same pattern over here. 1 nitrogen, 3 oxygens with a -1 charge. 1 nitrogen, 2 oxygens with a -1 charge. The one with the most oxygens ends in 8. The one with the least number of oxygens ends in ite. So when you look at this table or a table of polyatomic ions, if you group them together, the one that has the most oxygens in a group of 2 should end with 8. The one with least oxygen should end with ite. So sometimes people will try to remember all the 8s. Like I remember sulfate, nitrate, and I know if I needed the ITE version of it, is 1 oxygen less. Or vice versa, some people will remember all the ites and go, if I need an 8, that's 1 oxygen more. So sometimes people will not individually remember all these, but sort of remember either all the 8s or the ites. And because the only difference between those things is an oxygen, you could either adjust the formula accordingly. So that's a good way to kind of put them together. There's also groups of 4 that are related to each other, and this is the most common group of 4 right about here. And that is ClO4-, ClO3-, ClO2-, and ClO-. And they all have a -1 charge. The only difference in all of these guys is the number of oxygens. So that's a group of 4, which means if I break it right about here and go to the right, these are the guys that have the least number of oxygens, and they should end in ITE, which they do. So if we look, I'll just go down here to write it. This guy would be chlorite, and this guy would be chlorite, ITE at the end of it. Obviously, you cannot have the same name for 2 different ions. So even though they both end in ite, in a group of 4, the one with the least number of oxygens will also start with hypo. Very badly written, HYPO. So this is hypochlorite, and this is chlorite, which is this guy here, the ClO2-. If we go to the left-hand side, these are guys that have the most oxygens, so they should end in 8. So this guy would be chlorate, and this guy would be chlorate. So just like on the other end, you obviously cannot have 2 things with the same name. So in a group of 4 that has the most oxygen, it also starts with per. So this is perchlorate. This guy right here, ClO3 minus, is chlorate and chlorite and hypochlorite as we go this way. Now, that's the most common group of 4 that you come across. And as you might know, obviously that Cl is a halogen, which means you could swap out the Cl for a halogen, another one. So if I do, just for example, right above here, BrO3 minus, that is exactly the same formula, except instead of this one being called chlorate, it doesn't have chlorine in it, it has bromine. So this is what, as you can see there to the left, bromate. So you could actually swap out the halogen there, and it's named the same way. If you had BrO4 minus, as you can see here, that's perbromate. And again, you have the hypobromite as well when you look at it. So those groups of 4, the ones with the most oxygens in the group of 4 will end in 8. The one with the most oxygen out of that group of 4 will also start with per. The one with the least numbers of oxygens will end in ITE, and the one with the least number of oxygen total out of the group of 4 will be hypo at the beginning of it. There's some other things that are kind of put in there as well. For example, if we take CO3 2 minus, that is carbonate. And if we actually put a H plus in front of it, we get HCO3 minus. And HCO3 minus, as you can see here, that is what is known as hydrogen carbonate. So hydrogen in front of it and carbonate. Or it is sometimes called bicarbonate instead of hydrogen. So bi instead of hydrogen. So bicarbonate, hydrogen carbonate is the same thing. You also see that with sulfate and bisulfate, which I think might be here somewhere. Maybe not. But you'll sometimes see that with sulfate. So if you have HSO4 minus, that is hydrogen sulfate, or that is bisulfate as well. Now, the important part is you should also see that the charge changes. Sulfate, which is up here, has a -2 charge, but when you put that H plus on there, +1 and -1 gives you a minus, +1 and -2 gives you a -1 charge overall. So not only when you put that H plus on, the charge changes with it. Now, a vast majority of all polyatomic ions, like I said, does end in ate or ite, but there are some that ends in IDE. So you can see here, OH minus is hydroxide, IDE. N3 minus is azide. CN minus is cyanide, which is right here. So there are some that actually do sort of end in IDE, but a vast majority will have that ATE or that ITE sort of combination. So let's take a look at how to name some of these, give you a chance here, see what you come up with. Cross out my earlier stuff I was writing. So why don't you do... Once you named these guys here. And why don't you write the formulas for these guys? So names for the guys on the left, and then formulas for the guys on the right. We got ammonium sulfide, lithium hydrogen carbonate, and silver nitrate. Okay, let's take a look and see how we're doing. So looking at the first one here, again, we have a metal, which is iron. We have a polyatomic ion, which is nitrate. And again, we do want to figure out the charge on the iron because it is a transition metal, and we do need to figure it out. So again, we have one iron. When you learn those, if you don't know already, nitrate is -1. And again, there's 3 of them, which technically gives us a -3 overall. That means that my iron here should be +3, and this would be iron Roman numeral 3, just like what we did before, because it needs it for the charge again on the metal. And even though we have 3 of these nitrates, it is just going to be nitrate at the end, just the whole name of the polyatomic ion. Even if there's more than one, has no effect on it. Again, no prefix or anything like that. So you also notice when we write this formula here that we do have parentheses, and that's because we have 3 of those nitrates. And if we wrote it like this, that would be incorrect, because what that basically says is that we have 33 oxygens and 1 nitrogen, which is really not what we're looking for here. So whenever you do have more than 1 polyatomic ion, you do need to put those parentheses around it and a little subscript on the bottom to indicate how many you have. Coming this way, this is Cu, which is a transition metal. Also need to figure out the charge on it. We have 1 of these sulfates, which does have a -2 charge, which means to balance it out, my copper here must be +2 in this case. And that's going to be copper Roman numeral 2. And again, the whole name of our polyatomic ion, which would be sulfate. And again, the 2 for the charge on the metal, which is +2. Any questions on those 2 so far? Continuing down then is our K, which is potassium. So that is group 1, which means just like before, don't have to worry about charges or anything like that. So we're just going to use the whole name of it, which is potassium. Again, because there's a 2 there, has no effect on the name. CO3 is really CO3 2-, which is carbonate. And again, we would use the whole name there. And that is why the 2 is here, because the cation in this case is K+. And we need 2 of them to get us to balance out everything. Any questions on that there? Okay. Now, going the other way, when we have the name, we just want to get the parts and put it together correctly. Really, with polyatomic ions, they are really ionic compounds. So ammonium is NH4+. Sulfide, which is group 6, is 2-. So again, when we put this together, we actually need more of the NH4+. We need a grand total of 2 of them to balance out the charge. And because that is a polyatomic ion and I need more than 1 of them, I need to put it in parentheses with the 2 on the bottom. And I just need 1 of the S, and that would be the formula here. 2 NH4s, each at +1, gives me +2. 1 sulfur at -2, or sulfide, gives me -2, so +2 and -2. Lithium hydrogen carbonate, that's a lot of words, but lithium we do know is group 1, so it has a fixed charge of +1. Hydrogen carbonate is what we saw there just a second ago. It is HCO3-. So ultimately what you're doing is taking -1 and +1 and putting them together, and you will get LiHCO3 in this case. Lithium hydrogen carbonate, or lithium bicarbonate, it would sometimes be called. And lastly here we have silver, which again, transition metal, but does have a fixed charge of +1 always. Nitrate is our NO3-, also a -1 charge. So in this case, just need 1 of each, AgNO3. Any questions on any of those there? So the polyatomic ions will not be provided for you. You do need to know them. And again, you need to know the charges and the formulas so you can put them together correctly. Any questions on any of that? And as we see here in these examples, for the most part, probably going to end up with a metal. So really you could follow, as we talked about, the rules for those metals, type 1 or type 2, as to whether or not you need a Roman numeral or not. Okay, so let us continue on with our naming then. The next sort of topic of namings are going to be acids and how we go about naming acids. So acids are basically solutions that produce H plus in, or substances that produce H plus in solution. H plus are, when you talk about acids, when you take the next class, H3O plus, which is a hydronium ion, basically the ability to produce that is what makes something an acid. And when we name acids, it all involves whether or not there is oxygen. So oxygen is the key as to how we go about naming acids. So another important thing for acids is, because they are substances that produce a solution, acids will typically have the AQ, which is the aqueous symbol next to it. It basically means a water environment, essentially is what that means. So let's start with no oxygen. If the acid has no oxygen, it will start with hydro, something ic acid. So if we take HCl with the aqueous next to it, this has no oxygen, so this would be hydrochloric. I get that out there. Acid. If I had HBr with the aqueous symbol, this would be hydrobromic acid. So hydro, the anion being second. And again, it's that aqueous symbol here that distinguishes it between if you had just, say, HCl that was a gas. HCl that was a gas is basically H plus and Cl minus. And this would be hydrogen chloride. So again, that aqueous symbol is what distinguishes it between being an acid and not being an acid. And that's different than here if you had HBr. That wasn't an acid. Say it was a gas or something like that. You would call it hydrogen bromide. But if it is an acid, it will have that aqueous symbol. You should write the aqueous symbol, and it will be known as hydrobromic acid. Again, if you had H2S, that's an acid. This would be hydrosulfuric acid. Again, different than if you just had H2S that was a gas. That is known as hydrogen sulfide gas. So again, that AQ is important for it to be considered an acid, and you should include it there. And as you can see, if it is an acid, you should use hydro something ic acid. And that is specific for guys that do not contain oxygen. So what happens when they do have oxygen in it? It's a little bit different in terms of how we go about naming them. So let's talk about acids that actually do have oxygen. So if it is yes to the oxygen, it will contain probably those polyatomic ions. And as you remember, those polyatomic ions pretty much end in ate or ite. So let's talk about what happens. So if it's yes, and your polyatomic ion ends in 8. Your acid will be something ic acid. So HNO3, also with the little aqueous. NO3 is nitrate. This becomes nitric acid. H2SO4. SO4 is SO4 2 minus. This is sulfate, becomes sulfuric acid. Now you may be wondering about this too here. What makes something an acid is really H plus and some type of negative guy, right? So really the cation here is H plus. Sulfate is SO4 2 minus. It is still an ionic compound, really. So when we put it together, we need not one H plus, but we need two H pluses to balance it out. And that's why the 2 is here to balance it out. So just kind of like a normal ionic compound. The only difference is for an acid, that's always going to be your cation, really, is H plus. It's always the acid. Cation is H plus and something else. Now, if your polyatomic ion, and it does contain oxygen, ends in ITE, your acid will be something OUS acid. So HNO2. NO2 is nitrite, ITE. This becomes nitrous acid. H2SO3. SO3 is SO3 2 minus, which is sulfite. This becomes sulfurous acid. So if it has oxygen, it will probably have one of those polyatomic ions. And if it does have those polyatomic ion, if it ends in 8, it's IC acid. If it ends in ITE, E is OUS acid. You can see on none of these with oxygen, there is no hydro on either of these. So hydro is only for ones with no oxygen. So why don't you try here maybe? Why don't you try HClO4? Why don't you do HI? Why don't you do H2CO3? Okay, so since we're getting to the end here, let's take a look. So we see AQ, which is an acid. We see this, which is H plus, which is always a cation. ClO4 is actually ClO4 minus. That's perchlorate, ATE, which means that this should be perchloric acid. Again, it has the IC, and it even keeps this per part of the name, which is perchlorate. You still keep it. Again, no hydro here because it has oxygen in it. This does not have oxygen in it. So this is one where we would use hydro, where H plus is our cation, I minus is our anion, and this would be hydroiodic acid. So hydroic acid. Again, no oxygen here. That's why we have the hydro. And lastly here, again, our cation would be H plus, which it always is for an acid. CO3 is CO3 2 minus, which is why we have two of them here to balance it out. Carbonate, ATE, becomes carbonic acid. Again, no hydro on that one either, because it does not, it does contain oxygen. Any questions on those? Okay, so what we'll do is we'll stop. We'll take our 20-minute break. We will come back for lab. And actually, what we're going to do at the beginning is we're just going to finish out talking about nomenclature. We have one more topic to sort of cover in terms of naming. And then at that point, you should be free to finish or start, finish, whatever, work on your study assignment there, which is about nomenclature as well. So you'll get more practice. So what we'll do is we'll take our 20 minutes. So we'll start about 9:50 and we'll finish lecturing on this here. I think we just have one more little sort of area of naming to talk about. And then afterwards, you should be set up good to do your study assignment, which is all about nomenclature. So make sure you type here if you didn't do so already, and I'll see everybody in about 20 minutes at 9:50 in the lab entrance there.